My name is Emily Pillmore. I am a developer. We'll get more into my details soon, but I'm glad you all came because this is going to be a really interesting talk for everybody. I think Alex Konovalov and I did a lot of work in this area over the past year and a half. And it mainly stems from some folklore that we've seen in the community regarding parametric reasoning. And a lot of these techniques that we've been using sort of ad hoc in a way that kind of makes sense was prevalent everywhere. We saw it all over the place. And we had absolutely no clue where it came from, right? So the idea that like if I'm counting types or trying to refactor a type signature, I can treat functions like exponents or products like multiplication or coproducts like addition. That actually works, and that's a valid principle that everybody sort of individually discovered independently from one another over time with no formalization, no blog posts, no content backing it up or actually telling anyone what it's actually doing. And in fact, it's included in this guy right here on page 46 and 47. And it was the original question that we both asked. It was like, what's going on here? Why does this work? Which is really cool. So you can thank Sam's book for this talk and for a 6-hour workshop that we did at LambdaConf that's filmed in a sort of long format version of this talk, which is more in-depth and goes over a lot more of the sort of foundational concepts and really digs into the category theory, for example, which we don't do here. We do a little bit of category theory and we get you to where you need to be in order to do some basic reasoning, like figure out how distributivity works in a categorical sense. And then that's all you're left with, right? So if you want more, whenever the LambdaConf talks come out, ask John whenever that's going to be, some year, one of these years. Then we actually go into, for instance, the understanding a lot of these universal properties like currying and pairing as consequences of adjunction. And we write out the functors that correspond with that adjunction. And yeah, it's slightly more complicated and definitely out of the scope of this talk. So today, we're going to be building perspective as opposed to getting into the hardcore details of exactly what we're doing here. So we'll do some type arithmetic and then build the perspective necessary to understand how to parse what you're doing in terms of types and then sets, and then from sets into some category theory, and then understanding how to link the three in terms of reasoning, just natural intuitionistic reasoning. And then we'll bring it home with some examples, and you guys can actually see this in like at work. And hopefully this makes a lot of the sort of folklore and the algebraic reasoning principles that people have been using click. And we'll see examples of it along the way, so you'll know what I'm talking about. Right, so who am I? I am Emily Pillmore. I like to do a lot of math, and I'm slowly transitioning away from programming more into mathematics. So I've sort of switched from chartered mathematician and full-time programmer to just programming some weekdays and doing math most of the time. You may know me by the handle of Emily Pi. Go figure, that's my name. I run a few meetups in New York, so if you're based out of New York, come meet up. Or if you just want to participate and you're international, then we have a Discord where we run these things out of, and you can see our solution sets that I want to say we write up, but it's me. I am alone in that. I have to typeset everything. And if you want to join up with some hot action, come hang out. They're usually weekly or bi-weekly, and we hold them at my office, and we get free pizza and drinks. So yeah, all the slides that I host are at my GitHub for all these things, which I keep separate from my personal one, which is at the handle cohomology. which is an homage to my topological background. And I'm always happy to help answer questions, whether it's programming or category theory, type theory, or just mentorship or help for whatever reason. I got my start in Scala, let's say, 4 years ago, almost 4 years ago now, so about 3.5 years ago, with my first programming job. And I ended up reading Runar's Functional Programming in Scala back to back, and that's my basis for functional programming, which we've expanded with the Blue Book and then myriad other sources, right? And this is just Runar in general, what he has to say about the Red Book. Yeah, I currently work at a place called Cadena, designing a language and a couple of blockchains, and I do Haskell full-time. So we're going to learn how to count, principally. We're going to learn how to add 1 and 1 and figure out what that means in a few different contexts. Exactly. It's harder than it sounds. The foundation for understanding how to add 1 plus 1 is actually pretty deep, it turns out. But we all have good intuition for it, which is why I think we can present this talk at this point, because I think we're all familiar with functional programming to some degree, and we're all familiar with parametricity to some degree, and it's time to start thinking about these principles more holistically. And it actually happens to apply to multiplication and exponentiation, and even in limited settings, division and subtraction, which is a deeper topic, which we can do as an unconference, but there's a lot there. Fractional types and negative types are things in bidirectional systems, which are slightly more complicated than what we'll be doing. Yeah, so this is principally a talk about type theory, category theory, and constructive logic. We won't really be getting into any of the set theory, but I expect everybody to kind of know how to count how many things are in a set, so we'll briefly talk about it. And the whole viewpoint is a viewpoint called computational Trinitarianism, extended to quadratarianism or something like that. I forget how to say it. With hot, but if you want to look up like the NLab article on this, you can just paste in that search phrase, and you'll get some really interesting stuff. Right. And some of this mode of thought, well, not directly, principally related, you can apply to things like optics. It is mostly a perspective for reasoning and how to draw analogy in general with categorical and type-driven concepts, which I will be doing as part of an unconference, because I have some pretty cool stuff there that might make optics click for some of you. Right. And we'll be counting types. So for instance, if someone says, count how many inhabitants there are to the type for all A to A, so the identity type, the polymorphic identity, you know there's exactly one thing in there. It's the identity. How? And you'll be able to answer. Right. So there are two perspectives that we're going to split this into. The Leibniz perspective, which is the perspective of understanding when two things are equal. And then we can draw a direct analogy with the Yoneda lemma and find that there is a categorical version of this sort of thought about properties of different elements of types. And then we can draw the lines to Curry-Howard correspondence and then Curry-Howard-Lambeck correspondence. Right. And then we'll tie it all together with examples, so it's not going to be totally boring and me just lecturing the whole time. And special thanks to John for inviting me here. I think this is a pretty great conference, and I'll probably come next year, especially to the castle, which is really nice. It's nice. All right, so let's get started with some type arithmetic. We're going to take some things for granted just to start. And don't think too hard about this. Consider it like a synthetic theory where we just axiomatically state that these things exist and have these properties. So unit, we're all familiar with. It has exactly one inhabitant, right? It's just unit. It's just parens. And we'll denote this as 1, right? Or script 1 in this case. So that'll be the type with exactly one inhabitant. There's a type with no inhabitants called nothing. In Haskell, we have something called undefined. The type is void, and undefined is the inhabitant to this, which is sort of paradoxical in the sense that it doesn't exist. That should say void. Sorry for anyone who's being nitpicky about this, but that is a value as opposed to a type. And we'll denote this by script 0. Function types will be denoted a to b with an arrow. Sometimes we'll denote them by exponents, in which case b to the a means the type from a to b. Universal quantification is for all, or the symbol for quantification. And we're going to introduce two new sort of functions or morphisms or whatever you want to call them, syntactic constructs. The straight bars will denote taking of cardinalities, and the square brackets will denote constructing types with exactly a certain number of inhabitants. And these will be considered as scripts. So you'll see like script 2, script 3, and that'll be just the type with exactly that many inhabitants. Okay? Our calculus assumes we have finite coproducts and finite products. So these will just be either, which is the binary coproduct, or either of either, which is the trinary coproduct. And in the same way, you get tuples, which is the binary product. And then nested tuples form the bigger products. And we'll denote them with multiplication signs in the latter case. All right, so this is your tuple 2. And we also assume that our types are set-like. Right? So we're not going to get into weird edge cases. We're going to draw the distinction with set theory. So we're going to take the view of types as sets. Right. So that brings us to our first concept, isomorphism. So to say two things are isomorphic is to exhibit two functions from a to b and b to a, so that their composition is the identity. And we'll denote this by a compose b, or sorry, a tilde b, or a equals tilde. Right. So is everyone familiar with isomorphism in this case? We're nodding heads. Yeah, cool. Okay. Right. So what does it mean when we say inhabitants? For example, 1 plus 1 and 2, are they inhabitants? Are they different inhabitants of int? We'll have to figure this out. For now, let's just assume that we can tell inhabitants apart, and we can do this with a sort of discriminatory function, classifying different objects by a function from a to bool. Okay? We're not really going to use this much, but it's just a technical point. Right. So the real question that we want to solve for the remainder of this talk is how do we represent type arithmetic as if it were high school arithmetic, so that all of your sort of basic reasoning principles in high school arithmetic applied. And then what are the edge cases if this calculus holds? Right. So does 1 plus 1 equal 2? How can we tell? We can count. If we replace 1 plus 1 with our unit types, so 1, the coproduct of 1 and 1, then we can sort of count this type and we can show that it's something isomorphic to the type with 2 inhabitants. Right, so just counting units. Cool. All right, and this is just a point about referencing numerals by their scripts. Okay, so how about maybe containing values of type with 2 inhabitants? So for instance, bool, maybe bool, how many inhabitants does that have? And you can just yell out the answers if you... Yeah. All right. Yeah, so we're already here, right? Because maybe 2 is isomorphic to the sum of nothing and just, and however many things are in the just case. So you actually have 1 plus 2, which is, we can expand the coproduct and we get something isomorphic to 3. Right? So in general, maybe has 1 plus the cardinality of its type in the just case, many inhabitants. Right? And in the same way, we can enumerate bool, the product of bool and bool. right? We have exactly 4 inhabitants to this. We know bool has exactly 2 inhabitants, true and false, and we can enumerate the product all the way down to the, from true, true to false, false. Right, and how about exponents? This one's slightly more difficult. Right, if we have a function from bool to bool, then how do we count these inhabitants? Well, we can actually write out the functions, and we can see that, for instance, we have k1, k2 here, which are 2 versions of this function, and we can just continue on through k4, and we note that we're exhausted, and we have exactly 4 inhabitants to this exponent. And we can do the same thing with like maybe bool to bool. You can actually write out these functions, and you can see there's exactly 2 to the 3 many inhabitants. There's 8 inhabitants to this function type. Right. So in general, we see that we have b to the a many inhabitants, or cardinality of b to the cardinality of a many inhabitants. Right. So this behaves exactly like exponentiation, and we want to see why that is. Right, so here's a question. What are the inhabitants to these 3 types? This is a bit of a tricky one, and here are some edge cases, our first edge cases. How many inhabitants are there in 0 to 1? Right, exactly 1. How about 1 to 0? Right, yeah. How about 0 to 0? All right, okay, you guys are good. Okay, cool. So, right, so we've built this kind of table here where we can sort of see what we have corresponding with our number of inhabitants. And our mission is going to be to fill in the rest of that table. You can kind of see where this is going already, right? So we have these kinds of facts that we won't go through really, but I've provided some programs which actually compute the isomorphisms between these. And you can see them later when you see the talk slides, which are very complete, so feel free. Right. So here's the picture. Now there's one thing wrong with this slide, which we'll address later. Okay. So why do we care about this in the first place? Well, the principal reason is proving that a type T has inhabitants is equivalent to proving the theorem corresponding with T due to this correspondence. Now, one thing that you can get from this is if I know I have an isomorphism between 2 types of different size or perhaps compactness, then I can provide an isomorphism between the 2 and therefore replace one expression with another, which is potentially in a more compact form, and it helps compiler writers perhaps optimize for size or optimize for efficiency. And this is how free theorems work in the first place, right? You're noting the isomorphism between your types, and you're swapping them out at compile time with things that you know are equivalent. So this is how compiler writers execute their rules, their free theorems, and how, for instance, IDE writers might suggest hints based on like observational equivalence, just looking at what your types look like and suggesting maybe better types and more in convention with your language.
Question.
Yes?
Could you give an example of the types being isomorphic with different cardinality?
No, not with different cardinality. They'll always have the same cardinality if they're isomorphic.
So what's the difference all the time?
Between
Oh, you said
doing compactness.
Yeah. Okay.
So for instance, if I had A cross C plus B cross C, then that is slightly more memory inefficient than, for instance, C times A plus B.
Okay.
Right? Because you only have one coproduct in that case, and only one tuple as opposed to 2 tuples and one coproduct. But they're, you can observe that they're equivalent statements. And you can just go through all of your code, and you can modulo by that isomorphism, and you can eliminate a product for every instance. That's a pretty big win in a lot of cases. Right, so let's talk about the Leibniz perspective. When are 2 things equal?
When they have exactly the same properties.
Right, Paul, you know this. Yeah, so we've been using equality the whole time, but it's been a kind of convenient lie because we want to draw the distinction with high school arithmetic. But really, we're not really talking about equality in this case. And you can see this in this slide. Is 1729 and 12 to the 3 plus 1 to the 3, and just the statement, the first number expressible by the sum of two cubes in two different ways, are these all isomorphic? At what level? Are they equal? Well, as expressions, no, they're not. But modulo isomorphism, they are, when viewed as integers. And enumeration in this case is, in this sense, is kind of like taking an equivalence class of isomorphisms of a type and providing just like one representative to be your sort of representative as a finite set. Right? So in Haskell, I mean, this is how we would write isomorphism here along with these two laws, which show the two sides of the isomorphism are identity. Right. Now, okay. Yeah, so if A and B are isomorphic, then we have this nice property that if any two inhabitants are equal in my first type A and equal in my second type B, then isomorphism preserves these equalities. So this is a nice property to have. Back in the 1600s, Leibniz actually knew this, and he came up with this principle. So it's been almost 400 years since we've known this. For any x and y, if x is identical to y, then x and y have all the same properties, right? So in symbols, we have this statement. X is equal to y if and only is equivalent to saying for every property of x, if the properties of x are equal to the same properties of y, then we can call them equal. And this sort of places elements in context. And it says, if I can view all of those properties about one thing to be the exact same thing as another, so if I'm saying the same thing about two different things, then they're actually the same thing.
Shouldn't this be both ways?
Both ways for what?
Because this can have y being richer than x. So you claim all properties in x have an equivalent in y.
Mm-hmm.
You say nothing about all properties in y.
Well, you can just replace y with x and then flip them. And this is for all x and y.
I don't get that.
They just flip the.
Maybe you can't just flip them.
Yeah, you can. Yeah, because they're equal, and you're quantifying over x, or quantifying over x and y.
Okay, I don't get it.
Yeah, well, we can talk about that more later. Okay, so just to show some isomorphisms that we constructed previously. For instance, we could show that A is isomorphic to the product of unit and A. We can show that swap for tuples is an isomorphism. Reassociation in this calculus is an isomorphism. Yeah, and so on. And we can do the same thing with void and either. These are isomorphic with A. Swapping your eithers is isomorphic. And even reassociation of your coproducts is isomorphic. Right, so what are we really saying about our types? We're saying this. We're really just talking about isomorphism the whole time. Right. So this brings us to the question of what to do with set theory. What are the sets with the cardinality A cross B, A plus B, 1, 0, and B to the A? Right, so we have, in the first case, we have the sort of Cartesian product of sets. We can just count and sort of inductively prove this. Plus corresponds with the disjoint union of sets. 1 corresponds with the singletons, and 0 corresponds with the empty set. B to the A corresponds with functions of sets, right? The number of functions from any two sets, or between any two sets, right? So we can fill in another column. Great. But we're still left with categories and wondering how to draw a distinction between categories and our calculus. Right. So you see where we're going here. So some category theory. All of this is going to be expressed within some small bicartesian closed category. So we avoid basically all of our problems. Most of the time we're just going to be in set, so don't worry about it. We're just trying to get the sort of most holistic view of our calculus.
Question, what is a bicartesian category?
Right, so you have finite products, coproducts, and exponential objects, a terminal object, and therefore an initial object as well.
Is this basically a topos?
I don't think it needs to be a
Doesn't
topos.
have
Yeah. But it would be nice. I mean, we could just call it the strongest category you can come up with and just avoid all problems. I would leave that up to Bartosz to actually decide where we are, mostly because, yeah, I try and just figure out exactly what's needed, and I don't have the best knowledge of exactly where this should be. Right? So we come to the definition of category, which I think we've heard enough about from Bartosz and a few other talks. Categories consist of objects and morphisms. We have morphisms between any two objects with a domain and a codomain. We have identity morphisms for every object. And to each pair of morphisms, we can associate a composite, which is a morphism from the domain of the first to the codomain of the second morphism. Right. So for every category, we can talk about its opposite category, which is its dual, right? Consisting of the same object data, but with the domain and codomain of each morphism reversed, which gives you some nice reasoning principles, because every time you reason about a category, you're also reasoning about its opposite category. And in that sense, if you have, for instance, a theorem for all categories C1 through Cn, you're actually proving 2 to the n properties for every statement. So it's a very efficient theory, right? The data of a category is subject to some axioms. A function, a morphism from x to y has identities, or it's invariant under identities, right identities with its codomain, its domain, and then left identity with its domain, right? And for every composite triple, you have an associative triple. And between any two objects in a category, you can associate a collection of morphisms, which in our case is just going to be a set. But there are situations where, for instance, you don't always have this for free. Right? So that's what we call our HOM. So if I say HOM, I'm referring to this collection. Right? Yeah, so we're familiar with this. We're familiar with morphisms, identities, and composition. In Haskell, they translate into types A to B, the identity function id, and composition, which is just our dot. In Scala, they're roughly the same, where you have fat arrow, and then identity and compose spelled out. Right. So isomorphisms in this context become a pair of morphisms, which are inverses of each other. And they produce identities on either side, depending on how you compose. Right. So if x and y are isomorphic, we'll just say congruency. Right. We can also talk about the size of a category, which I was just talking about a little bit. A category is small for our intents and purposes if it has a set's worth of morphisms and objects in its category, in the category. Locally small if we can only say that the HOM between any two objects is a set, and then large if it's not small. Okay. Go figure. For our purposes, everything is small. Right? just to make things easy, unless I state otherwise, which I will state later on when I give you the definition of Yoneda. Right, so functors are mappings between categories subject to the following data, where to each object C of your domain category, you associate an object F, C, and D, and a morphism in D for every morphism in C, which preserves composition and identities. Right. Right. So in Haskell, we represent this as functor of F, and we represent just the data we can, which is the mapping of functions into this new category, which is still the same category in our purposes because every functor is an endofunctor in Haskell, and the same as in Scala. And if you place maybe parentheses around this portion of the statement, then you can see exactly how we're sort of lifting a function into a new function, right? And the only thing we have to make sure of, which is something that we can't enforce unless we're in a slightly stronger language that can express laws, is the preservation of identities and the composition principle. Right? So functors that act uniformly on arrows are called covariant. Functors, or if a functor is mapping to or from an object or an opposite category to a non-opposite category, the distinction is rough, then one calls these functors contravariant. It really depends on the action of arrows in this case. Right, so saying F is a contravariant functor from C to D is the exact same thing as saying it's a covariant functor from C op to D. When it matters, I'll just tell you which one. So we've already seen a functor here, and it's not really apparent to most people. But what do we mean by cardinality? This is kind of cool, and this was actually a big help in our understanding of this calculus. I mentioned that we're really talking about sort of isomorphism classes where we pick a representative, and in fact, cardinality is a functor from the category of isomorphism classes of finite sets into set, where you pick a representative of this isomorphism class. Right. And as an important example, we have, for instance, the covariant and contravariant represented functors, which are usually called the covariant and contravariant Hom functors for any object, where you just lift it into reader or co-reader, right? So we're familiar with these, right? So you just, reader is variant in its A, so you have reader T, and that expands to a function from T to A, and the instance is just by composition, post-composition by some F. And for co-reader, it goes the other way, so it's actually a contravariant functor which composes by precomposition. Right. So to each functor is associated a family of data, a family of maps from each object C to objects FC of D, and likewise between morphisms. So this kind of immediately asks the question of how can we translate the data of one functor into another? Right. So in order to see this, you would have to imagine sort of the holistic picture of what's happening here. First, we would need two functors of the same domain, right? Because we need to translate this data from one to the other. And second, we need a way of associating each C and C with an FC and D, and a translation from FC to GC. Right. So we have a construct in category theory called natural transformation, which does this for us. It has, or it's a mapping between functors, which usually we say alpha from F to G, where it's subject to the following data, to each C of C, a component map from F evaluated at C to G evaluated at C. And in such a way that the following square commutes with any morphism from C to D. All right, so we're just building these squares and telling us how we translate between each object that is acted on by F to each object acted on by C, and how they compose. right? So this is the thing that we really want, this naturality condition. And in Haskell and in Scala, it looks almost the exact same. We represent this as the following data. A natural transformation from f to g is the type for all a, f of a to g of a. So we represent it by the action of component maps. And then we just have to make sure that the naturality condition works out in this case. Right? Which basically just means, you can compare this with this. It's the exact same thing. Right. And a natural isomorphism is simply a natural transformation in which each of those component maps are isomorphisms. Okay? Right. And you might note the use of notation here for a functor category. This is slightly more in depth. We won't get too into this. It might be a little bit frightening. It just means the category of functors from C to D with morphisms natural transformations. Okay. Right. We also have a notion of sort of special objects in our categories, which we've actually seen and we've been using this whole time. And we determine their sort of special status by their relation to other objects in the category. An object C is terminal if it has exactly one unique morphism from any other object to that terminal object, right? So if the HOM is a singleton ending at that object, then you have a terminal object. And dually, if the HOM is a singleton starting at that object to any other object in the category, then it's an initial object in that category. And you have uniqueness of these objects, obviously.
But that's not for every category, right? That's for the special.
Yeah, well, it's not always a given. You don't always have a terminal or an initial object.
Is there a name for it when I have them?
When you have them?
Yeah.
I don't think so. I'm not sure. I'd have to defer to that. Defer for that. Yeah.
What would be other examples except the singleton? What would be other examples for categories where terminal or
Right. Okay, so this is a slightly tough question because small categories tend to have very uninteresting terminal and initial objects. Okay, for instance, in set, the terminal object is a singleton and the initial object is the empty set. But in groups, the initial object is the terminal and the initial group, so the trivial group, which is just the group consisting of the identity, right, and nothing else. You have more interesting things like, for instance, we won't get into it, but in some sense, products and coproducts are terminal and initial in the right category. But they're slightly more complicated categories to construct, and we won't get into it, but we can talk more about that later. For our purposes, we really just want to note that void is our initial object and unit is our terminal object in this category. Cool. Right. So for every type A, we kind of have this data associated with these objects, right? We have exactly one type of morphism from A to unit and one morphism from void to A for any A. And you can enumerate kind of what these morphisms are. Const of unit in the case of unit, and absurd in the case of void. Right? So in the case of absurd, this is kind of like saying, I'm just going to pick out a very concrete element of A, and that will be my element of A. You can't really do this generally for all A. Sorry, no, that wasn't true. You have to pick a specific inhabitant of A in order to make this work, because you can't introduce void. So you just have to choose and place some element of A. Right. So in the same way that we have terminal and initial objects, constructions for products and coproducts in category theory follow suit, right? So we have special objects in this case. And in the case of a product, I know for yesterday's keynote, we sort of denoted this by the syntax of A cross B, but really what you're talking about is a special object. a special object with the property that if it has two sort of morphisms coming out of the object to some C and some D, and then if any other object, say N, with morphisms to that C and that D, then P is a product if all of those morphisms from N factor through a unique morphism from N to P, right? So you just kind of fill in that F. And you note that FC and FD in this diagram is a composition of PC and PD with F, right? So you're just talking about objects here with special properties.
So P is a terminal object, right?
In a specific category, not always the case in general, right? So if I'm talking about set, it's not, right? Right, and we're familiar with this. This is just pairs, right? They have this property. And coproducts act the same way. It's just a special object with injections, which factor through a unique morphism out of the coproduct, right? So we saw this. And likewise, we have a nice diagram which composes in just the opposite way of the product. Okay. Now we're familiar with these because IC and ID are usually called left and right. But in the literature, you'll usually see in L or in R. Right. So the diagrams for these products and coproducts define their universal property. In an imprecise sense, like I said, this kind of just says that these constructions are initial or terminal themselves in the appropriate category. That should say or terminal. Now we can consider morphisms to and from products and coproducts, beginning with products first. And usually what's good about beginning to understand your object is to look at mappings to and from that object and see how it interacts with others. From the universal property, we saw that for products, at least, mappings into the product gave us one property. And for coproducts, mapping out of the coproduct gave us another property. And now we can start looking at, for instance, morphisms from a product and morphisms to a coproduct. Right? So for instance, for a function in the set of functions from the product to any other object, what's the data necessary to produce a C? So if I have A cross B to C, then how can I produce C? Right? So F specifies an element, F of A, B, and C. Therefore, we have to require that the data of partial application gives me a function from, for instance, in this case, A to C. Right? So then I just fill in my A for that, that tuple, and then I produced a C. Right? Right, so it's equivalent to sort of specifying a function from C on B to a function from A to C. Right? And in this case, we can show that it's isomorphic. And we're all familiar with this data, right? This is currying and uncurrying for this isomorphism. Right? Right, and we can play the same trick for coproducts. We can look at how they map out of this coproduct, right? We can look at a morphism A plus B to C, and we can note that if I have just an A case, then in order to get a C, what I would have to do is produce a function from A to C. But if I had a B, I would also need to produce a function from B to C. So in effect, in order to make this morphism work, I would have to have a pair of functions, one from A to C and one from B to C, right? One for each side. And we end up with another isomorphism here. And we can exhibit all of these isomorphisms. I just won't do it explicitly. Right. So we have a nice principle called pairing here, and I think we're familiar with sort of the end of Bartaj's talk where we spoke about this pairing principle, right? Which was either, and I call it pair when we produce an either out of the tuple. But really it should be unpair, pair and unpair. Right? Similarly, you can do the same thing with maybe a function to a product, right? I won't show this, but you could deduce something like A cross B to C is equal to, or isomorphic to A to C cross B to C. Right. Right, which brings us to a sort of perspective, how we've been reasoning about our types. We just look at sort of morphisms to or morphisms from those types, and it determines a kind of property of that type, right? And we can kind of fill in the rest of our column here, or columns, where we have a correspondence between types and sets and their number of inhabitants, and now with categories. Right, so in the case of types, we have sort of objects of our category, and products are the sort of usual product in a category, and coproducts are the usual coproduct. And then we have morphisms in C for functions, and terminal and initial objects form our sort of void in our unit in this case. Right, so we're sort of still building intuition here. What would the perspective of Leibniz look like in a category theoretic setting? Right. Just to remind everyone, this is what we're going with for Leibniz. Right. And we can see that sort of how we've been reasoning about products and coproducts and individual properties of objects. We look at morphisms to and from these. So we kind of have a good candidate already for how we can reason about objects in a Leibnizian way, right? We can look at, for instance, morphisms from or to those objects, which gets more to the point of the person who asked about what about the flip side of things, which is true in this case. We do have to consider both morphisms to and from. But it actually turns out to be, I think, equivalent in this case. Right. So if we just take a look at an isomorphic pair, so for instance, A is isomorphic to B, then we have a theorem in category theory associated with this, and it's called the Yoneda embedding. In this case, it's the sort of covariant Yoneda embedding. Is it covariant? No, contravariant Yoneda embedding. Yeah, because that would be C opt to set. Yeah. Right. So, sorry, what?
Natural isomorphic.
Right. Yes, these are naturally isomorphic because these are two functors, right? This is the covariant represented functor. Oh no, this is the covariant.
Natural isomorphism.
Oh, so okay. Remember natural isomorphism? I mentioned it in just one slide a while back. Yeah, we can do a quick. It's totally fine. I don't mind. We're actually on time, so we're good. So natural transformation from F to G. I forgot the notation. Sorry. Associates a map from FC to GC for every object in the image of that functor.
Okay, so a natural isomorphism is just a natural transformation. That is an isomorphism.
An isomorphism for each of its components. Yes. Yeah. So when each of these component morphisms mapping these each object at F and G, when each of those are isomorphisms, so for instance I have an isomorphism between every pair of FC and GC, then I have a natural transformation. So basically the horizontal arrows, when those are isomorphisms, that's a natural isomorphism. Okay? Cool. Okay, great. All right, so we can prove this statement, and I won't go through it, but I have the proof in here for anyone that wants to see in the slides later. For instance, we can start from the fact that we can locate bijections, which pick out an inverse pair in these Hom sets by choosing X to be something clever, and then we can produce a bijection between these two sets, right? And then we can go the other way by noting that functors preserve isomorphisms, right? Right. So we mentioned in the previous slides about functors being represented by an object, like the co- and contravariant represented functors, which are sort of reader and co-reader, if you remember. Right. So we have a notion of functor which relates an object to perspectives of this object, morphisms to and from the object itself. Right. And this kind of gets us a perspective, like objects exist in relation to other objects in category theory. Right. You can imagine like the cardinality of a set as being the set of morphisms from the singleton to that set. You have a to the 1 many inhabitants to that set, and that's exactly the cardinality of A. Or you can look at the power set as a morphism from, or the set of morphisms from A to the type of 2 elements, or the set of 2 elements, and you can, the set of those morphisms picks out every subset of your A, right? So these properties that we associate with a lot of the types and sets that we work with are encoded as morphisms to convenient and special objects, right? And this is a controversial statement from a friend of mine who's currently doing a PhD in category theory. Everything in category theory can be proven as a combination of Yoneda lemma and category sets. Now, I'm not sure how true that is because I don't have the experience yet, but he swears by it, and I will give that to you. And then we'll let Bartosz cry out if he doesn't like it. Right, so this is the Yoneda perspective. 2 objects are isomorphic if and only if the functors represented by them are naturally isomorphic, or at least part of the Yoneda perspective. Right, and we can talk about representable functors in general. A representable functor is a functor from C to set, along with the following data, a special distinguished object C that is said to represent F, and a natural isomorphism between that functor and the covariant or respectively contravariant represented functor at C. So in the case of the contravariant case, many people call it like co-representation. I don't really see the point. Representable functors from C op to set and representable functors from C to set are the same in my mind, except you have to take care to note which functor you're actually isomorphic to, the co or contravariant represented functor at C. Right, and we represent this by an isomorphism in Haskell between F and the reader at C, right? So that's all this is saying. If you view it from the lens of iso, remember we had to and from, and they were sort of inverses of each other. You're doing the same thing here. You're just saying f at x is isomorphic to c to x. Right? And then there's some, this functional dependency. We can, that's a point that we won't get into, but the functor determines its representing object. Right, which brings us to the actual Yoneda lemma, which is for a functor from C to set, when C is locally small, or at most locally small, every collection of morphisms, like we said, every collection of morphisms between any 2 objects forms a set. It's just for sizing constraints. Then F at the representing object is isomorphic to the set of natural transformations between reader and F. Right. And we won't go into proving this, but it's a pretty important statement, as you'll see operationally when we actually go through the exercises. Right. But one of the nice parts about this is you begin to note that the natural transformations that we talk about are completely determined by the identity at C. Which means we kind of have a sort of pseudo-inductive principle going on here where the identity of the representing object determines the rest of the set associated with that natural transformation. One of the interesting ones that someone noted to me was, for instance, if I look at groups and I look at a functor from group to set, and I note that there's a representing object in the integers, then I can think about this functor from group to set as sort of associating the unit 1 with the image of, so associate the unit 1 with some element in my set, and I can sort of generate the entire set by looking at the image of that identity. Right. Which is a little opaque, but for the mathematicians in the audience, that's kind of interesting. Right. And it's natural in C and F, but we won't get into that. For our purposes in Haskell, we note that for all x, this is saying a to x to f of x is isomorphic to f of a. And likewise, for all x, x to b to x, f of x is isomorphic to f of b when f is contravariant. Right. Now this is an operational bit that we can use to our advantage in many different ways. And some of them are not apparent at all. A lot of it takes a lot of getting used to. But anytime you've reasoned about a parametric type, you've probably been using Yoneda under the hood, and it's that ubiquitous. Right, so this is all the data that we have. And we're going to get into some exercises where we can actually just shout out how many inhabitants you see, whether you have any questions. Right, here's a nice proof of using Yoneda of the distributive property that Bartaj and John went over yesterday in a more holistic way. We can just apply Yoneda, curry, pair, uncurry, and un-Yoneda, and we arrive at the exact same conclusion in 5 steps. So Yoneda is pretty cool. Right. Here's proof of the isomorphism. We won't get into it, but yeah, we've written all this stuff out, and it's true in Haskell at least. Right, so that brings us back to the original question. How many inhabitants does for all a to a have? And how do we prove how many inhabitants it has? We already said that there was 1 in this. Well, here's the proof. A is isomorphic to 1 to a. And then we can take the functor in play here to be the identity. You'll note that this is, with the identity, exactly the shape of our statement of covariant Yoneda. No, contravariant Yoneda. And id in this case is here, so id of a. And then we can reduce. We note that the isomorphism is f at the representing object, which is 1 in this case, because we're for all a. And this is just isomorphic to 1, right? Likewise, we can show that for all x and for all a, if we have a morphism from the tuple of a and x to a, which is kind of like const, but an uncurried const, then we can show isomorphism with the functor a to a, right? And we can reduce back down to the identity to 1. Right, so that's proving that const has precisely 1 inhabitant using Yoneda. Likewise, we can show that a to a, or a pair of a's to a, we can use the same trick. We can apply unpairing in this case, and we can note that this is exactly the same thing as a function from bool to a. And applying Yoneda with identity again, and we end up with something isomorphic to bool, right? So there are precisely 2 inhabitants to this type signature. Here's just a fun one, which is a little bit more complicated, with a slightly more complex functor, a to c to b to a to c. We can note that b to a to x is actually just the composition of readers, and this is a functor. And this is isomorphic to reader from a to b to a, which is exactly flip const, and flip const is exactly isomorphic to 1. because there's one inhabitant in const. Modulo flip, which we didn't prove, flip is an isomorphism in this case. Right? And we can show that composition can only be done in one way when you're working with polymorphic types. So for all A, B, C, composition, modulo some clever use of Yoneda, has exactly one way that you can compose. Is everyone okay with that? Questions? Okay. We're pretty much on time, so I'm glad we got like time for comments too, because I blew through this. Right. We can also show some type signatures that are maybe a little bit more complicated, that are totally counterintuitive, actually are inhabited. So the pair of functions from A to not, which are not inhabited in and of themselves, is actually inhabited when you consider a morphism from that pair to nothing. Right? It actually just reduces to the identity. And I don't think there was any interesting use of Yoneda there. I think that was stuff we all covered before. Right?
But the last slide is so counterintuitive. Right?
Yeah.
Like, there's no way I can implement that. And then you're just saying it's just identity.
Yeah. It just reduces to identity.
You're screwing with my brain right now.
Right. That's the point. This isn't straightforward calculus. There are edge cases.
No, I understand, like, each step is like every little step that we've seen in the previous presentation, right? So if you publish that, I can trace every line in this slide.
Right.
But earlier we proved that a function from a pair of x to x has two inhabitants. Isn't that in an instance?
Let's see. Hang on. It might be a typo, but let me look real quick. 1 and then pair 2 to A. Okay. No, because if you replace... Yes, you're right. Sorry, this is an error. This should be a 2 at the bottom. Sorry.
Isn't this one because there are in the tuple there are exactly none on both sides, so we can pick only one? Maybe this is the case why it's 1 instead of 2?
Oh yeah, no, because the third from the last is const. And that's const with 0, so that, no, this is fine. Yeah. Yeah,
Also,
this-
because it's a tuple, there's no way to create any other inhabitants of that tuple.
Right.
So it's 0.
Yeah,
It's 1.
there's exactly one. Counterintuitive. Edge cases at 0. Right. And we also have a sort of Yoneda for propositional equality here. I won't call this Yoneda. It's Yoneda with asterisks, right? Yoneda in the correct category with asterisks. But without restrictions on F, we can have a kind of Yoneda with respect to propositional equality, where for all A, if A is equal to X, and we have a morphism from that equality to F of X, then that's isomorphic to F at A. Right? And we can show that this actually works. For instance, when reasoning about type constructors, where we know certain types are equal to our, like for instance in this case Z, if we know X is equal to Z, then we can sort of exploit this this type constructor calculus and arrive at an answer that this is just identity. Right? So what about types that have A occurring in positive and negative focus? Like for all A to A to A to A, right? Well, we can actually talk about recursive types using this calculus, right? So we can show that, for instance, the fix type, so if you've ever seen Haskell's fix, where it's just sort of rolls indefinitely, we can show that this is isomorphic to something that looks like the recursive type notating the natural numbers, right? So if you look at the function and squint hard, this looks like a starting element and a successor function arriving at a final type here. And this is exactly like a church encoding of piano arithmetic in like structured sets, right? Right, and we can even generalize this calculus to containers, right? So, for instance, a lot of things are containers, controversially or not. Like maybe is sort of like a singleton container here. Lists can be shown to be a sort of power series expansion at x, where I have, you know, precisely one thing, which is sort of our unit, precisely one x, precisely two x's, or precisely three x's, and so on. And you just sort of build up this sort of product of x's, right? We're going to notate that by sigma of I to denote the sort of size of this container. Yeah, so a list of x is sort of isomorphic to sigma I of x of I in this case. And we can show that the free theorem for f map at x is actually the exact same thing as expressing a dependent function from a certain size, n of type nat, to a list of finite sets of that size, which is kind of cool. Applying Yoneda all along the way. Right? So you end up with something like this. And actually in Idris it does give you this. Right? So for more exercises, we did do a 6-hour version of this where we got really in-depth. That kind of felt a little bit in-depth, but we really got in-depth with about 100 exercises detailing this. There's also a blog post on Alex's blog, just alexknvl.com. You'll see our work on counting type inhabitants. Yeah, and slides are going to be available today. Like I've already got these up.